I feel like I need like a Mr. Rogers style intro for these videos some days. Like I walk in and take off my coat and fold it and change into my house sweater or whatever he does. Um, I guess he changes shoes, isn't it?
Yeah.
That's what he does. Okay, Arvo. This is gonna be pretty interesting. There's so many parts of the way that we structured, like I came up with this outline and then I didn't realize like how well things were actually going to segue one into the next, because then it turns out that, we've done a lot of vase mode stuff and now we are going into meta vase mode. Like we're doing vase mode on vases to work with untyped nouns at that level. So there's some interesting ramifications of being able to do that. Let's see, let me switch you to this view and get I wish this system had like a just switch views, instead of set it up from scratch every single time you change your context. But we were stuck with whatever the galaxy brains at Zoom came up with. All right, there we go. That big enough? Or would you like it bigger? Okay. All right. Today we're going to be talking about what's called the main sequence Arvo, or mature Arvo. The distinction arises because when you start Arvo for the first time, or when you upgrade Arvo, you actually have to work with an immature Arvo that doesn't have the same full implementation of everything that you do in the mature state. But most of the lifetime of Arvo is spent as mature Arvo if you aren't booting or upgrading. So it makes sense to start there. Arvo is essentially an event router. And so most of what we're going to be talking about is what does it mean to handle events, route events, operate on veins. What state does Arvo actually maintain? It has persistent state and it has ephemeral state that it has to keep track of. And then finally, we'll start talking about how OTAs actually work. And then next time we'll go into the boot sequence and more details on what an upgrade looks like before we turn around to the runtime. Now, a good place to begin thinking about Arvo is, what is the design intent of Urbit as a system? And if you do some Harry Seldon psychohistory on Urbit and you're trying to figure out, what were people thinking, why were they acting the way they acted? So Curtis was writing phone operating systems in the 90s before he started working on Knock in 2002. And anyone who's done operating system work at any level has run into the fact that operating systems are event spaghetti, that actually tracking the causal chain for any particular computation is fairly difficult. Now, Unix and Linux do have, threading and fork protocols, so you can keep track of parent and child processes to some extent. But there's a lot of other computations that take place on your system that are ephemeral and essentially impossible to track. And so it's very difficult to audit what's going on when you do this. So Arvo is designed to avoid that. And what it's going to do is it's going to keep track of an event as a pair of cause and effect. And the cause is a chain of every place that this has been. And then the effect or the action is, your desired thing. And at the bottom of that, that causal event ultimately was something that you did on the host OS. So we can call it a Unix IO event. Maybe you're not necessarily running Unix, but it's a POSIX-like event where you have a network request or a terminal input or a file sync or a timer event something happens that triggers this whole chain. You're typing on the keyboard, you receive information over AIMS or over something else. The difference that Arvo has, and why Arvo is an operating system, is that it pushes every step in the path that the request takes onto a chain forward until it gets to like the actual action or effect of that computation. And then it pops everything back off to route results all the way back to the caller at the end of the day. So you can track this whole process forwards and backwards as you work with this. And so you're familiar with, at a high level, Arvo is an event handler, and it's just sort of a ratchet in a state machine. So it's this life cycle function that is a function of its history, and it produces a state. And every time we have an event, that event is, history +1, and we have a new state that results from that. And so we're going to use the terminology that a move is a cause and an effect, or a cause and an action. I'll probably say it both ways. There is a formal move type that we'll see that specifies the call stack and the action, so you can associate those things. That's different than an event, right? An event is a completed move. It's the event is what results in the updated state. And that updated state is then the subject for future computations. And part of event completion is that it gets recorded immutably in the event log history, which Arvo itself doesn't actually know about. Arvo doesn't know about the event log and history. That's a runtime convention or protocol, whatever you want to think of it as, heuristic. Arvo's amnesiac in that it sort of only computes against its current state. That's the thing that it knows in the world. And this is why you can do things like chop an event log. You actually don't need the entire history. Older, but you needed the entire history to recreate the current state if you ran into some problem in your memory corruption or whatever happened. You had to replay that whole event log. So what a chop does is this stores the actual state of Arvo at some epoch, and then you can play events forward against that reference point, that milestone, to get you back to the current state. And Matt has been doing a lot of work on event logs and epochs and everything right now. Didn't you say that Ver 3.0 is ready to come out?
Yes, epoch system was merged earlier this week for Ver, which bumps it to 3.0 because of backwards incompatibility
with the Loom. Or so what is backwards incompatibility?
It means that if you were to run Ver 3.0, your event log format changes on disk.
Okay, so
and
2.0 was the Loom format changed, and 3.0 is the event log formats changing.
Correct.
Okay. So is there going to be a migration that has to take place?
There's a migration, yes. It migrates the disks in the .urb faz log directory of your peer to a new format that includes epochs, which are directories that are numbered with a pat UI of the event sort of segment, which it represents, the epoch represents, or holds actually the data for. So if you were to go back and run an older Ver binary after running 3.0 and after running that migration, it wouldn't work.
Mm-hmm.
Yeah.
Okay. So when I get to Arvo's event log structure in 2 weeks, I'll have to make sure that I'm up to date on what that looks like at that point.
Sure. Yeah, let me know. Happy to help there.
This has actually been an interesting aspect of writing this Arvo lesson, was just realizing how much of my knowledge about Arvo, like Arvo has actually evolved a fair bit in the past couple of years since the last time I took a serious look at it. But we'll start with the high level, what are the guarantees the system's trying to make, and how these things operate, and then we'll get down into code as we proceed today. So All right. So if we're talking about like what Arvo's trying to do, we know it's an event handler. It's a move router in a sense. Um, there's some guarantees that it tries to make as a system. So one of them is that it's a solid state interpreter. So if you look this up, no one uses this phrase outside of Urbit. So Urbit is the answer as to what is a solid state interpreter. And so if you read the white paper and you look around, you find that essentially this is the way of describing Urbit's grounded ability to acquire and specify state as this sort of reproducible, auditable quantity that you can use as a basis for computing. The event, once committed to the log, it's immutable, it's permanent, it's never lost. And so you can always use it to recover the state that you have now. Ted, is that when we say solid state in that way, is that being used in the same way as when we talk about solid state subscriptions?
It is, although it has a bit of a different meaning. Like it's the same concept, right? It sort of implies the same, feeling, right? And like the general lack of moving parts. Well, solid state interpreter at this layer mostly refers to the fact that the interpreter itself is this stateless thing, at least formally, and so all it does is run knock, right? And knock is frozen, and so you have this thing that's sort of like you can send it an Arvo and an event, right? And it'll run, knock on that, and then output, effects and new Arvo. And the thing that does that is this frozen thing that's stateless, that has no moving parts.
And what makes Urbit different as an operating system from basically every other major system, and I think a lot of what gives it this solid stateness and this frozen function feel, is that no required information in the state of the operating system is ever stored in RAM alone. Like obviously we're doing a lot of computations in RAM, but the subject and everything is getting written down to disk and is fixed and auditable at any point.
Yeah, well, to be pedantic about it, the event log gets written to disk, which can be used to reconstruct the subject. The subject generally is partially in memory, partially on disk, but can be lost, and that's okay because it can be reconstructed deterministically from the event log, right? So
Yes.
all the stuff that's in Arvo, like in general, as a programmer, you want to think of it as if it's in memory, basically.
The origins of operating systems and the breakdown of the bicameral memory model.
Yeah.
All right. So we have a solid state interpreter. One of the things that it guarantees is atomicity. Yep. Which is that events that are interrupted, you lose power, you control C, whatever happens, never happened from the perspective of Arvo. And so the computer's deterministic, it's transactional. There's a place in the docs you can find it talking about this as an ACID database, where so that's kind of what I'm pulling from here, which is that your operating system becomes this well-behaved database that you can reason about, and you can count on certain guarantees being available to you because of that. But the consequence of this interpreter and atomicity together, is we're playing these events, we're always processing these moves to move forward, which means that it's very compiler heavy. We're always compiling and building Hoon and Tanakh expressions throughout the lifetime of all these processes. And so that'll come up in the structure of Arvo later on as well. The other ACID guarantees, we have consistency, isolation, and durability. So yeah, so atomicity, only completed moves become events. Consistency is every event leads to a new valid state. You can't get the system in an inconsistent or irreproducible state. Events are isolated. So Arvo is non-preemptive and it's single-threaded, and the events are performed sequentially, meaning that everything is an isolated effect. And this has some ramifications with the way that we handle move orders, for instance, which is part of the breadth first versus depth first move order discussion that has apparently been going on for years from what Phil was posting about earlier this week. So we'll talk more about that too. Look at that. And then durability is, related to the solid stateness, where you can't reverse an event. Completed events are permanent and immutable. This doesn't mean the same thing that any completed transaction survives permanently, right? Because there's a couple things that can happen. One is, clay is referentially transparent, but it can tombstone, right? So you can actually mark data as lost. And from the definition of referential transparency, we're not actually claiming that the information will always be available. We're claiming that it will never change, that new data will not become available at that address in the scry namespace. And so that's why we can tombstone things, and it'll crash on an access rather than produce different information or anything else. And then similarly, you can have events in your history that revert changes that have been made to your state, but this is still part of this history function that's played forward. And when you're calculating against the subject at the current time, the state at the current time, you may not have visibility in the things that are there in the past. Okay, so let's start Arvo with then the structure of Arvo. So at the heart of Arvo, this is the knock expression that we are evaluating ultimately. We don't explicitly construct it very often. There is some initial boot stuff that basically does this in pure knock, like in the Eden life cycle formula. We'll take a look at that next time as well. But functionally, this is what you're calculating. So what does this mean? All right, does someone want to talk me through, like, read this knock? So there's some subject here that this is going to get evaluated against. Like, what is this knock saying?
Is this saying take the head of the subject and evaluate it against the tail of the subject?
It's saying take the
yeah.
Well, it's saying take the battery of the current subject to yield a new battery. That's this.
Yes.
That's this one. And then take the payload against the current subject and evaluate that, and then evaluate those two things together. Yes. And so this is saying process the next event. It receives the event, it's appended to the subject, and then you're processing that event to produce the new result. And so Arvo, go ahead. Okay. So Arvo is an event processor. And so Arvo is obviously much longer than this, and it's full of event processing and routing machinery to make things happen. There's also some plumbing on the vein side that we'll run into doing this as well. And so there's a number of types that, if I can fit on my screen, I'll be very happy about. That'll work. Is that still large enough to be legible from line 22 on? Okay. All right. So we have our like type, we have our formal definitions here. So our root thing is a move, and a move is a duct and a ball. We called it a cause and an action, or a cause and an effect. So a duct is a list of wires. And so the causal history a single entry in the causal history of a move is a wire, right? And a wire is an alias for a path. So it's just this identifier that lets you point to, here's the part of my system that this came from, and therefore when I send this back, here's the information that that part of the system needs to reinterpret that returning gift. I write ball out two different ways here. Line 28, the first line is the compact version. This is what you'll actually find if you look in arvo.sys or sysarvo. But if you expand it out, you get a more a more complete description of what this dynamic kernel action looks like. And so ultimately, it's going to be one of these four types here. Something is a hurl, a pass, a slip, or a give. Most of the time, we're thinking about passes and gives. We're passing something forward along this causal chain because we need to continue the request, or we are giving it back, we are returning it along the causal chain. This is, by some large fraction, this is most of what you're thinking about doing. There's a hurl, which is your error handler that you're passing back, something's gone wrong. And then there's an interesting one called a slip, which is a lateral move, which is basically feign to be someone else in the system and pass this forward. The response I've gotten with this as I've talked to different core devs about it is that it's kind of hacky, but there are a couple places in the system where this is still fairly justified. So we'll look more at that one in detail. If you look at older docs, there's also a description of something that would be a Unix event that relates to things that are generated at rock bottom as Unix tasks. And apparently that system was never really clearly specified or as formal as what that implies, because you can get arbitrary injections from the runtime into any vein as pass notes. And so, did something come from Unix? You sort of don't care in the sense that you need to track it in the ball and in the type of the dynamic kernel action here. So the ball is what we conventionally think of as the computation. This is the thing that we're requesting, is where this goes, and then there's a note and a task that tells you sort of how to pass these things down and keep working with these things. We're going to have a few others here that we're going to run into incidentally, like a card and a cask. These are tagged untyped events. Arvo does a lot of untyped things. And so when we talk about vase mode, we're going to be spending a lot of time in vase mode or in second order vase mode as we process these things. And the ultimate result of this is that we need to define a meta or a maze. I've noticed that in practice, people often use the word maze to refer to the meta vase itself. Formally, it's either a vase or a meta vase. But most of the time when you say maze, it sounds like you're not actually worrying about which one you're talking about, because you're just, a maze is an untyped vase. It's a vase of, it's not only a vase of vase, but one of the things it can be is a vase of vase, where you're stripping this type information off. These are our types. Now, Arvo defines structurally 4 different standard arms. And so if you go read about the runtime, if you look at the plunder criticism, it shows up in a few places. People talk about, like you're running Arvo on Ver. So Ver and Arvo are pretty coupled to each other. What we're referring to there when we say things like that is that Arvo has an expected noun shape, right? The same way that a Gall agent has to have a certain shape, Arvo has to have a certain shape as a noun. What this means for the runtime is that it expects to receive a core with certain arms, because these are how it's going to systematically interact with each one of these nouns as it processes things. So Arvo is going to define 4 standard arms today. So there's a load arm, see standard arms. All right, so there's a load arm. This is a kernel upgrade, and the neat thing about one of the neat things about these arms is that the way the runtime accesses them is they have canonical addresses in the noun. So your load arm is at +4, and you can find it here. So this is what Arvo is going to use to pass itself from the old world into the new world with an upgrade. So we're not going to do a lot with load today. There also, if you look at the older docs, there was a come arm that was used for when you had type changes, because you actually had to do things in a completely untyped way. But you can reproduce this with multiple calls of the load arm. It sounds like it's just a touchier process there. Do you want to say anything about that, Ted? Joe was talking to me about this removal of come and how we don't really envision changes to type, for instance. Okay. There's a wish arm. Wish is functionally, this is accept a core, parse against the standard lib, right? So Zeus, essentially. This is instrumentation for your runtime access. So this is how the runtime is parsing these particular cores. When you think about Urbit eval, so there's an Urbit eval command that is not actually exactly this for a subtlety we'll get into later on, but conceptually, this is your Urbit eval. You can throw information into Arvo, ask it to parse it against Zeus, and it'll spit this value back out to you. There is a peek arm, which is your read-only vein access. So this is a scry at 22. And there is a poke arm, which is accept and process move. Okay. This is the only arm that actually modifies Arvo, Arvo's state, as opposed to Arvo replacing itself with load, which is not done very often. So if we want to process a move, we're going to send it to Arvo's poke. So this is what Gall would be doing, for instance. If you send a vein request or something like that, Gall is accepting this, passing it to Arvo through the poke arm, and then it's getting passed around through that. Every arm possesses the same structure, which means that as the Arvo kernel grows and changes, the main event dispatcher can remain the same. So when you merge the build vein forward into Clay, you didn't need to change anything about Arvo to do this. The only thing you needed to change about Arvo is it maintains a registry of the veins that it knows about. So only affected veins and calls to those veins needed to change. Everything else, Arvo is, Grand Central Station. It's just making sure that everything gets to the right place at the end of the day. Now, if you go look at sysarvo.hoon, which you may as well pull up because we're going to be poking around in it a lot now. One of the complicated things is that there are actually 4 Arvos in this system. So if we go look for things like how many wish arms, actually we only have I wonder if they actually have different names than the others there. Oh, we don't have a come arm anymore. We have a peak arm. Yeah, there's a lot of peak arms that show up here. But there's going to be several Arvo cores that are present here. So one of them is the larval Arvo core. This is at the very end of the file. And this is going to be used when building Arvo for the first time. And so this is an outer core that has dummy arms for some of these things, like peak doesn't, peak just returns an empty value. It doesn't do anything because with the larval core, when you're booting a new Arvo for the first time, you haven't yet shed this stage. You don't want any peaks to be processed. That's not what you're trying to do with the system at this point. So we'll look more at that next time with the boot process. There's a structural interface core, if I can remember how they should have written down what the line numbers of these things. It's not not this one. Anyway, rather than hunting through this file, I'll just give you what the four cores are. All right, so there's a larval core for booting. There is a structural interface core. This is your main primary mature core. What it actually does, though, it provides a formal interface, and then it's actually going to call out to two other cores, which are going to be the implementation core, which is the operational core that carries out particular computations and dispatches. So you can have simpler code in the structural interface core and then call out, and then the section 3BE core, which sounds like a government office entry here. And this is containing a lot of helper functions that are sequestered for security. This has a lot of arms in it that you don't want in the 4-arm prototype of Arvo. Like how do you parse a scribe path? How do you negotiate versions? Essentially, it's Arvo library code, but it's only pure functions. So this one's kind of the workhorse, and then this is the formal interface specification. That's your baby Arvo. Yeah, Y3BE. So if you go back to the original Arvo code back when it lived in hoon.hoon, the whole system was organized with names and labels. A lot of Hoon and Zeus is still labeled this way, but in early Urbit history, Arvo lived in hoon.hoon, and so it lived in section 3BE. That was the point in the Hoon cores that it occupied. Arvo only has Hoon in its subject and itself. It doesn't have the veins, or I guess it probably has lol because it needs to know about the interfaces for the veins. But it does not have Zeus or the veins in its subject, which plays into, if you're going to rebuild Hoon, then you need to rebuild the things that rely on Hoon. If you're going to rebuild Arvo or Hoon, then those things get rebuilt. So when you start doing core dev with a lot of compilation, where you're making the change starts to matter more and more, because you have to start having to recompile more and more inner cores in your system. Now, Arvo maintains, this is Arvo state. Arvo maintains persistent and ephemeral state. Urbit likes for things to be stateless. It likes for things to be pure functions. So it tries to sequester the state explicitly as much as it can to particular cores. And this is, in Arvo, the state is the entire kernel in operation, but we can catch this information persistently between this Arvo state is this is the persistent part, and then there's going to be ephemeral move workless that'll get used in various contexts to keep track of what's actually going on. So there is a definition here of pit that we're going to be using to refer. We're going to be referring to it when we keep a cache of specific types. This is kind of an interesting syntax here. So .is refers to the subject of is, and then we are zapgaring it. So what we've done is we've captured the code prior to this point in Arvo as a vase. If we go find this line in, I just want the zapgal dot is. Where's my dot is? Oh, they changed it to part. Interesting. Okay. Well, that's what I get for working from the docs instead of the actual piece here. So now it's part instead of is. I don't know why that name change happened, but it's referring to the code in Arvo above this point as a base. And so then we're going to have a set of cached types, type, duct, path, vase, to save on recompilation. So we're going to be referring a lot to these things. We just want to keep a cache of them around and not recompile them every time we need to use them. There is a verbosity dial. This is the laconic bit. So when you bar verb, this is the value that you're changing in Arvo. How much information is it printing? And then it knows about entropy and your ship. Both of these are they're part of the identity here, but they're referring to quantities that are ultimately provided by the runtime. We have the vase of the standard lib itself, so the vase of Zeus, and so we can use that. And then we have a list of veins, and these are labels and veins. So just these two pieces together here. Now, as an aside, before I move away from the structure stuff of Arvo into talking about veins and move handling, I wanted to comment on wish as Urbit eval. So Urbit eval means that you can send code. I don't remember the exact syntax for it. Does anyone remember offhand what the syntax for eval is? Something like this. We can throw Hoon expressions at it from the outside and get them to evaluate against Zeus. But they're just sort of single op events, right? They don't change anything. They don't do anything. It's just saying evaluate this standard piece of Hoon. If we go to, let's see, I don't want clay, I want libvar. So in libvar, there is a wish arm. And so this is actually, you look at the shape of what we have from 3.16 onwards. This is an Arvo shaped wrapper. And it's doing the same move with pit where we're invasing the current subject. And so we actually need to go up and look and see what's in our current subject to evaluate this. And it includes the Ethereum and Azimuth libraries. So functionally, when we Urbit eval, we are causing it to slap against the current subject the ream of the text input that we're given here. So in vase mode, we have a vase of the current subject, which is Zeus plus Azimuth plus Ethereum. And then we are slapping whatever statement against that and returning those values back out. Actually, fantastically, look at the lark notation in that response there on line 326. Sorry, one moment. Excuse me. All right. Yes, so anyway, here's the Arvo-shaped core. When we look at pills, this var library, and this in particular, this Arvo-shaped wrapper, this Arvo wrapper, is the outermost layer of the ivory pill. So when we run things against an ivory pill, this is what we're running them against here. All right, let's see. Arvo, yeah, that's what I said. Right, like this is what eval uses. That's what I'm saying. This Arvo wrapper is what eval uses, and so yeah, the ivory pill. That's how we're getting to the ivory pill, is through this wrapper, which is kind of neat that you can make an Arvo shaped wrapper and then just interact with that and pass things through. Vase mode in action. All right. Back to Arvo.Hoon. We had a line that was veins equals, where's my, sorry, I'm looking for my state definition here. Oh, these things have all been moved around. Okay, actually, okay, that's another one. Interesting. See, this is the problem. Arvo's always like it's changing. There's more things going on. So it's a map now instead of a list. It used to be a list of pairs of labels and veins, and now it is a map of a term, which is going to be your vein label, sen A, sen B, and a trap of the vase. So we've made it more explicit than the vein type. We actually have a trap of the vase. Interesting. Why does this say while we desire it? Are we just pattern matching on the poetry of this statement here? Kind of interesting. Okay.
Well, yeah, and then in general, this is the larval state, right? Where we don't wait, is this the larval state?
This is a grub, so yes.
Yeah, right.
I'm actually trying to find the actual state. I guess this is the actual state of the veins here in the soul.
It's called soul.
Yes.
Yeah, soul.
Soul.
Right. So basically, the larval state is just we're hanging on to all the different pieces that will become the soul, but we don't have all of them yet. We get them one at a time in events, and so they're all kind of units, right? So while we desire it, it's like we while we're still waiting, while we still want them because we don't have them yet.
It's funny how we have these occasional bursts of poetry in the kernel. It's always fun to run across those.
Mm-hmm.
It's like there's the whole maybe it's in clay. There's that whole section where there's like this. Yeah, it's in the clay scries. There's like these errors on the scries that are like these long statements, and they're all the same length, and they're like these multi-word sentences. Some fun things like that. Okay. All right, so a vein is a map now instead of a list, which is fine. Functionally, it's basically the same thing. We look for grow. Here we go. Here's our mapping to our current known veins. And I'm not in develop, I'm in an older vein. And so this would also feature like if you're working against develop right now, for instance. But that's a new change. So a vein ultimately is it's a trap of a vase. Trap of a vase? Maybe it was a trap of a vase, but ultimately it's a vase that describes an outer gate which produces a core. The vein state is the gate that wraps the core that has the right standard arms. And when we operate with veins in Arvo, it's going to be doing things explicitly in vase mode. So if you want to look at the skeleton of a vein, which we'll do obviously we're going to do a lot more with veins. This here from this part here, this is a skeleton of Bane. Partway down, you can see that there is a gate, and then there is a core that is produced by this gate. Is a ket what? So I believe that it's iron, if I recall correctly. So there's some state stuff that's defined for every vein. Every vein does maintain a little bit of state. These are the things that it needs to know about the world. And we're treating it the same way as Gall state. We're head tagging with a version number and everything. We're bunting on that. And then we're producing a gate, and the gate needs the information in particular of roof. Okay, we'll come back to roof in a minute. But what's produced by it then is a core that has the right shape. It has a call arm, a load arm, a scry arm, a stay arm, and a take arm. So every vein is going to look the same way. They're all going to have 5 standard arms. This is what Arvo knows how to talk to. So stay is the state of the vein. Like if you're going to do an upgrade, this is your on save. Load is your state migration. It's your on load. Call is an incoming task. So this is what Arvo is using to send you information, to send you a task as a vein. It's going to come through call. take is going to receive a response, a gift, right? Like you get something back. It's actually not a gift at this point, it's a sign, but we're getting this thing back in our take. And then scry returns the veins state. Roof is an interesting piece here because each vein is going to receive a roof in its function call. This is what handles scry. So you remember when we were operating with fake knock 12 and everything, we had to pass it a gate that could handle, I think this was in Mink, we have to pass it a gate that can handle a scry. And ultimately, this is what's happening here is we're passing this roof gate into the particular vein. So this is what's going to give you a bridge between .ket and the look scry handler in Arvo that we'll look at a little bit is this roof gate. So the problem is that if you gave agents a scry handler that was a gate closed over the entire vein state, then anyone would be able to access anything in any vein state. So .ket and Mink want to mediate the access so you don't reveal the entire state of the system in the subject, because you would be able to get untyped permissions-free access to any part of the noun in the subject. And so roof is kind of this way of wrapping that information and giving you this smaller constrained closure rather than a closure over the entire vein state to do this. This is also where I guess look is where scry lost comes from. So let me find look. Yeah, there's your scry loss. So if a scry fails and it sends a hurl back, then you have to deal with these pieces here. Yeah, I'm actually curious now. Yeah, so a roof is a room of a vase. I don't know what a room is offhand. A room is a namespace. Oh, okay. So this is namespace stuff. Yeah, so it's a gate, right? Like evaluate it in this particular context. Well, we're going to talk about the caching in a minute. So there's some caching with look as well from Arvo. So we'll come back around to that. Let's go back to, yeah, so Bain defines these things. It knows how to deal with its own kinds of, at some point at the top of, yeah, it's not in here, but at some point it tiscoms Bain so that you're actually able to, when you refer to particular pieces like gifts and tasks, it's actually going to be a, let's see, I guess, yeah, like there's a task. So this is actually a Bain task, for instance, rather than any other kind of task. And so if we go look at lol, we can see what the interface for each one of those looks like. That would be a, let's find. Yeah, so it knows about gifts, it knows about tasks. These are the kinds of things that Bain knows how to operate on. And so you still get the strong typing and everything that Who normally gives you. So when we come back around to the veins next month, this is kind of the place we're going to start with is what does the vein actually know how to do, right? Like what are these tasks? What are these components able to do here? All right. From Bain's perspective, then, if we look at the two arms that are interacting here, there's a take and a call. All right, so stay and load are state migration stuff. Scry is a read-only peek. So we have a call and a state. So Bain can receive a task or a gift. These are where you'll recall in the docs there's this little picture that is vein A sends sends a note to Arvo. Arvo sends a task to vein B. Vein B returns, I guess I should put it, vein B receives, no, replies with gift. Yeah, that's right. Replies with gift. And then vein A receives sign from Arvo. So it gets, oh, thank you. It gets really complicated to keep these things straight. And so we just kind of elide all of this when we're, you know, at the app school level or whatever. But from Bain's perspective, from a Vain's perspective, I'm saying Bain with a B and Vain with a V, but you know, that's fine. It can receive a task or a gift. These are the kinds of things it knows how to get, are a task or a gift. Anything sent out is a note or a sign. So if you issue a call to Bain from Gall, you're going to have this life cycle. So let's say you have a Gall agent. So this is going to send a card to Gall, and this is a card agent Gall. This is not the same as a card, as the untyped card stuff that's labeled in Arvo, which is also slightly confusing. That we end up using card in two contexts there. Gall is going to pass a note to Arvo through Arvo's poke. Then Arvo is going to pass a task to Bain through Bain's call. Then Bain is going to have its internal state. It's going to do the thing it gets. It's actually requesting the runtime to send it a wake up note when it needs to do something. So it has some runtime specific operations that are kind of internal to it, and there are some, you know, Arvo needs to receive this from the runtime and pass it to Bain and so forth. We're going to skip over that. But when it wakes up, so then Bain is going to send, it's going to give a gift to Arvo through Arvo's which arm? So if we're doing a move with Arvo, which arm are we using? Only one Arvo arm that handles moves. So it's going to be poke as well. Yeah. Then we're going to have Arvo give sign to Gall through Gall's. So call is how you receive a new request. Here, handle a task. Take is going to be how we receive a response, how we're actually getting this response back. And then Gall will pass card agent Gall to agents on Arvo. That's your full life cycle, eliding what happens inside of Bain as we're passing these things around. Arvo's role in all of this is to receive something, act as the mail clearinghouse, and pass it to the right place, make sure that it gets there. Now, we still haven't gotten into how are we evaluating these things, or how are we updating state of Vains or Arvo or whatever else. So we'll come back around to that. The other thing I wanted to talk about before we do that is, so we have a pass and a give, and we've seen how both of those work. We need to talk a little bit about a slip. So a slip is like a pass, and you can slip any card that you can pass. But what pass says is push the wire on the duct, right? Add to the causal history of it, transfer to receiver. What a slip says is don't push the wire on the duct, and transfer to receiver. All right. So what you're saying is, I have this, I'm not going to alter the wire. I'm not going to alter the call history of this. I'm just sending it somewhere else. So what does this mean on the return? If you slip without pushing on the duct so that control is given back, where does control go back to when it returns?
Whoever sent you the duct. So it skips the vein that slips it?
Essentially,
Okay.
right? You're just saying, pretend like I'm not here.
When would you want to do that compared to passing it? Like for like Gull and Bane, would it do it there, or?
So there's I've been able to find at least 3 places where this is used. One of them looks like it might be necessary. Like Joe was like, I mean, and if you look at the docs, right, this is code smell. Like you don't want to use this. It's not preferred. It basically the argument is that it violates layering,
Mm-hmm.
and it breaks your abstraction because you're just sort of pretending not to be someone else. So it shows up in the subscription lifecycle, for instance. It shows up in the init tasks when you are starting a ship for the first time, which only happens once. So, not a big deal because you're doing it once in this very controlled environment. And it happens in a Clay initiated Arvo upgrade. So when we talk about OTAs, these are, that's where it's going to show up. I don't know if I'd call it consensus, but definitely like a viewpoint I've heard expressed is that when we switch move ordering from depth first to breadth first, we can probably clean up a lot of the slip functionality, treat it as legacy functionality, and clear it out. I don't know if we'll be able to eliminate slip, but we'll be able to simplify some places that do use it.
Okay.
I don't know. Ted, do you want to add anything about slip there?
It's not used that often. Clay uses it at the moment to continue a commit after a kernel update. So if you try a commit to base, then Clay will first look if it changes any files in the sys directory. And if it does, then it pauses the commit and fires off 2 moves. One to Arvo to say, hey, Arvo, you might want to update yourself, which will then go and update Arvo and all the veins potentially. And then also the second move it emits is it slips a pork back to itself, and a pork move tells it to continue the update. So that's to trigger itself to keep going. But the important thing is that you want to keep going on the same duct, right? Like you want Clay to be activated with the same duct the second time as it was the first time. So it starts the commit with one duct, and then when it reactivates itself after Arvo upgrades, it wants to activate itself on the same duct. And so if you had used a pass there, that would add a new wire. It would push a new wire onto the duct. So that would be different. And then if you tried to give, for example, subscription updates on the current duct, it would come out wrong. You'd have to give them on some other duct, right? So that's what slip is for, is if you need to reactivate yourself or something else, but at the exact same duct as you're on right now. It's a questionable feature. Joe has been itching to remove it for a while.
Mm-hmm. Yeah, Joe is the one giving me the rundown on it. Yeah, he's definitely bearish on it. There's kind of related to this stuff. There's the old Unix task. If we look at lol, we can find some related things. Yeah, so there's a Unix task type here that defines this subset of expected tasks. Like these are things that you might be getting back from the runtime as well. Cancel a request, resize your terminal, type, right? Simply like awake is a simple one. You ask the runtime to set a timer. and pass this back. The way that veins work now with conn, C-O-N-N, this type is not actually really necessary anymore because you can inject any arbitrary task. I mean, between lick and conn, K-H-A-N, you can instrument everything. And so this is sort of less relevant than it used to be as a way of thinking about Earth and Mars divisions. Okay, so a little bit more. Okay, so that's kind of your first round of here's move mechanics, where we're passing these things around. Let's now go down into code and look operationally at what's going on with this. So Arvo only knows how to glue things and route things. It knows the veins by labels and it knows them by their interfaces, but it doesn't know anything about them. So Arvo's formal state is to be a gate to operate on an event to produce the next state. A vein, if you look at what Arvo thinks a vein is, it's a pair of a vase and a worm. So the vase is going to be the type and the noun of the vein. Like that's your vein state. Veins are compiled against Zeus as their subject. But like you have this vein. A worm is going to be a cache so that we don't have to recompile code every time we want to interact with veins. Everything we do with veins is going to be done in vase mode. Any vein call is going to be a slap, or something related to it. Yeah, so if you look at slap, call gate is a slap. Assemble a door is a slap. You're going to find these pieces everywhere, and there's some other related things that are untyped operators that are analogous. Like there's a slum that's like an untyped slam. Yeah, there's a slur. I think there's some others there as well, but we're doing everything in vase mode here. And so there's a couple of engines that are present here to do this. So there's va and wa. Va is less interesting in that it's basically just plumbing to handle vein operations. So it knows how to do untyped slams together, right? So here's a slam without sample type. So we're ignoring type and we're just slamming things together. So we're doing untyped vase mode operations here. And what happens when you switch to mazes, from vases to mazes, is you are operating in untyped vase mode now, because you could be working on the vase of a vase. One of the reasons this is necessary is you might be making changes to the system that alter type. Like you might be doing pretty high level operations on pure nouns, and you don't want to dig down deeper and be constrained by sort of conventional Hoon here. So this is a place where we have gotten into namespaces and meta namespaces. That's what a rook is on the plow here. For this Arvo side interface to working with veins. Like I say, va is mainly plumbing, and it is slamming things together untyped way, but that's basically what it's doing. It's just it's a vase mode operator. Wa is, I think, kind of a more interesting vein. This is the worm cache. So remember, a vase was a pair of a vein was a pair of vase and worm. So the worm cache is part of Arvo's state, and it's manual memoization. So what we're going to do, let's find the definition of worm up above. All right, so it's a nest, a play, and a mint. So it's a set of pairs of types that nest. That's what nest is. It's a map of type and hoon to type. And it's a map of type and hoon to type and knock. And so what you're doing here is you're basically saying that I can store what I've seen before with types and hoons and produce the knock without running the compiler. So if everything in vase mode is running slaps all the time, if all the vane calls are vase mode slaps, then Arvo has to run the compiler all the time. This is really slow, right? Like this is bad. So the worm cache is the way that you're going to keep all of your first-time computations and store them in this cache. So let's go down to WA. And it's a door. So we're gonna put the veins particular worm in the sample of the door. And then we have cached nest calls. We have cached gate calls. We have open. This is a manual send sig here, which is kind of neat. And essentially, so what the problem this is solving, this is the worm cache. The problem that the worm cache is solving is that every time you call a vane, there are three possibilities. One is that it's not cached, the call is not cached, and that it fails, the types fail to nest properly. And so this is you're in this case, you're going to produce a manual printf. Like this is a failure case here. And that's what this slog stuff right here in nest is doing. This is a manual printf that I'm spitting out. This is your need have. When you have something fail in type and you get a need have statement, this is your need have. You notice anything weird about it? Why are we doing all this? We're in untyped mode. We don't have any faces. So everything we talk about has to be done in Lark notation to find those values, which is kind of wild. Like this is why we're so deep in just operating on raw untyped nouns now that we can't even define faces that we can use to access these values anymore. I think that's a neat place to be. Another option is that we're not cached, succeed on nest, in which case we want to we're going to produce a pair of no and WA cache. So that's the case where that's this case. No, that's no, that's not that one. Where's our? I think it might just be that we're doing this over and over again. Yeah, nets is our typeless nest stuff. Looking for an explicit modification to the WA cache here, but I think it just gets returned and then Arvo builds it in when it gets the worm back. Well, I guess these are doing that here. But anyway, what you're doing is you're telling it it's not in the cache. I'm doing the initial calculation and I'm returning the value to you. And then the third case is that it's cached, in which case you want to produce, yes, I'm in the cache, and actually produce the worm cache. Here's my value. These pieces are being done manually. You know, we don't have type information, and so we can't just send hep, send sig, these values, we actually have to manually build the hoons. Here is our call to the default buck arm in the system. All right. This is how we're calling the buck arm when we call a gate. We are actually calling the hoon AST of limb and buck together. Now, why buck? This is the answer that everyone wants to go back to and say, why? Sorry, I'm trying to open your terminal here. Like, why do we talk about buck in a gate? Why is the default arm buck? Let me run a Zod here. I'll make it a little bit bigger for this part so I can fit my Zod at the bottom. All right. So send buck is the empty term. It's the empty pat TAS. So the reason we call it a buck arm is because when we are actually pulling it by name as a term in the hoon AST, that's buck, that's 0. We're pulling null. We're pulling sig. And that's why when people ask this question, I'm sort of, my answer is sort of like, it's going to take a long time to get you to the point where that answer makes sense to you. Okay, let's see. Some other things of interest in here. Let's see. There's slur is a neat one. So slur is slam a vase with a maze. So this is calling neat instead of nest to check things because neat, where's neat? I think these are actually alphabetical here. Yeah, so neat is your type checker, and based on whether you have a vase or a meta vase, that's what each gives you is that head flag of a PAM or bar. Based on whether you have a vase or a meta vase, you're either doing a typed nest check or a typeless nest check, which is looking at structure. All right, neat is pretty cool too. Or no, yeah, neat goes into nets. Nets then is running the nest check with slum instead of slam. So there's slum. This is your untyped slam on a raw knock. So this is how you run a raw noun as a gate without type information. This is Urbit's equivalent of close to the metal here, because we are just running nouns. We have a noun. We are running nouns. So for instance, what's happening is Arvo does something like it runs the scry arm on a vein. And it's going to receive back a vase of unit cage, right? This is our standard thing. And so we have these multiple levels of nesting, and we end up like unwrapping these as sort of like a manual zap gal, because right, unit cage means we have a unit of a mark and a vase, and you have to extract these values out to operate on them, or you can operate on them untyped, which is kind of the alternative to doing a zap gal. So you can either do a zap gal and push everything as we're elevating our dynamic values into our static context, or we can say we're going to throw away type information and we're just going to work on the raw untyped noun. The only reason this is not insanely dangerous is because we trust our veins. right? If you were doing this on nouns you received anywhere, this would be a problem. But we're doing this because we trust the veins, we trust the things that are built locally, and we have a lot of checks upstream to make sure we're not doing crazy things that are going to nuke our system. We're also going to construct these with raw events. So there's a raw event type, which is an ovum. Yeah, so this is sort of a move is a history of these values. An ovum is a raw event. That's basically like it can be a card or a curd, which is a typeless card. I'm not actually seeing curd in here anymore. I wonder if they moved that out somewhere. Okay, so Arvo maintains a worm cache for every vein that's built when the vein is initialized. What's going to change is we're going to take the worm cache out and we're going to put it in the runtime instead. Matt, remind me what the rune is. It's sig. Is it sig cab? The runtime memoization. Sigless. Sigless, yeah. So this is what's going to happen is with the new Sigless, and we can memoize at paths, we can move the entire worm cache into the runtime, and we should be able to get like constant time lookup and everything rather than looking these things up in balanced tree maps, which is going to be much slower. So one of the big wins we can get is going to be in speed is moving all of the caching out of Arvo into the runtime. You get a pure, simpler Arvo, and you get better performance out of doing that move. Matt, do you know if you're going to be involved with that change at all?
For the worm cache? Yeah, Joe just mentioned it yesterday.
Okay.
Yeah.
He's probably thinking about it because I was pumping him for info about this.
Mm-hmm.
So, let's see. There's an aside on Mic and molding that I can do. The rest of the lesson is I've got kind of 4 little grab bags of topics here that are worth covering as asides. One of them is OTAs. Let's talk about Mic. All right. So Mic, you give it a value and it coerces to that type, essentially. The vein interface is strictly typed. And by using a metavase, you can punch a hole in the type system. Right. So this is actually how you do vase reduction. For instance, a vein can pass to Arvo to get into like this double vase mode, like the vase of a vase. And then Arvo will collapse that back into one vase mode and hand you back the value. And this is the manual vase reduction that I was talking about a minute ago. One of the reasons that they used to have to do complicated things about vase reductions and molding data was that the mold system in Arvo used to be a total system. What this meant was that if the input mismatched on a mold, the mold would not crash, it would bunt. Now, from a type system perspective, the nice thing was that you knew that you would always get the correct type back. But the problem is that you don't know if you actually failed to coerce the type. So you're like comparing it to the bunt and saying, did I get the bunt back? All right. Joe Bryan described the mold system at this point as a pile of hacks because of some of the consequences of that. So in 2018, they introduced structure mode. And one of the changes that came from that was if your input mismatched, then the mold would crash. So now molds crash. So if I give it a value that cannot be operated on, then it actually, it crashes in the metacircular runtime, the user space knock interpreter, and I get this Hoon expression fail back. And so MICMIC was your crash. MICMIC was your fixed point assertion that guaranteed validation. This was the way you crashed in the old bunt system. After you introduced what was then called spec mode and is now called structure mode, molds do this already. And so MICMICs actually don't matter. They're completely superfluous. The only reason MICMICs are still around is so you can go straight into structure mode in the first entry of a value. So those two are identical statements here. COM, foobar, applied to foobar, this switches this into structure mode as we saw before. And this automatically takes its first value as a spec or in structure mode. That's the only reason MICMIC's still around. And so other than that, we actually should probably just get rid of MICMIC and use COM to switch into structure mode when we need to do that kind of operation. Now, I use MICMIC too much to coerce things, and I'd have to think about what that would do to the way I write Hoon. But nominally, it's superfluous at this point because of the way that types and bunts and everything get handled. Runtime connections. If you're, we're going to get into the runtime in a couple weeks. There's a couple of functions that are interesting if you want to go poke around in the runtime and see what's going on. U3 surf work, apply event and produce effect is what is actually happening when we process an event. Like if we're doing a replay, for instance, so you can see sort of mechanically what it looks like to load, apply, and produce a new state. And then U3V poke sure is how you inject an event into var and save new state. So they're kind of similar to each other. They give you a couple of different perspectives on what's going on. U3 surf work is the playback of the history, and then U3V poke sure is this is where a new event comes into the event stream for the runtime. So we'll come back to those later on. All right. Imminent on the roadmap, breadth first move ordering. We've heard a lot about breadth first move ordering lately. There's a couple of PRs about that. So Arvo currently orders moves by depth first. And so this means that when you have an event, it looks like this. I'm going to shrink it really small because it's just kind of a visual. Actually, you know what? I shouldn't shrink it small. I should just turn off word wrap. There we go. All right. So what this means is that depth first means that if you're given a work list of moves, when that first move produces a move, you process that move next. And if that move produces a move, you process that move next. And so you go down the tree of consequences from one move, come back up. When you get to the top, then you go to the next move in your work list and go back down. And so you end up with this system where you're sort of going up and down in your duct back and forth as you're producing these values and you're moving around. The same code with breadth first looks like this. Notice that it's using numbers at the front instead of bars, but conceptually it's the same thing here. And so what's happening in this case is you process, you have events 1, 2, 3, and event 1 produces event 1, 1, or event 11. You would process event 1, event 2, event 3, and then you would process 1, 1, and this 1, 1 produces a 1, 1 and a 1, 2. You process both of those before you process any of the daughters of those, and you go all the way down. The argument that's been going back and forth is how much this matters. Almost all of the code that we write is agnostic to this. when you're local and you emit a work list of cards in Gaul, you are guaranteed that those cards will resolve in order. But if you're doing something remote, you are not. And so sometimes there are hacks you have to do if you really need things to be ordered a certain way, because you don't know remotely if they're going to be evaluated in the same order. But with system upgrades and some other changes, this starts to matter. So for instance, if you generate 4 facts from dojo to hood, should they happen right after, one right after another, or should their children happen before the next move happens? With dojo, for instance, this makes a difference, because if I do something here with hood that invokes dojo, it's reentrant on dojo, then dojo might emit more facts, and those facts would be resolved before any of the things that I already had on the stack. And this is one of the reasons that your textual output from things in dojo sometimes looks like it doesn't make sense in order. It's because these children of the reentrant dojo stuff are resolving before any of the other things that you typed into dojo get handled. The appeal of switching to breadth first move ordering is that moves will be processed in the order they're emitted, and it makes it easier to reason about them. Depth first ordering violates this, because you're generating moves that you don't know about that'll be processed before you process the rest of your moves here at the end. What is particularly interesting about this, and this derives from a conversation that Phil was talking about in Minder Folden's group recently, where Curtis actually reached back out to Phil to argue against switching to breadth first move ordering. And they are now arguing about this. Like, this is interesting because I mean, the buried lead there is Curtis is paying attention to Urbit core dev again in sufficient detail that he's making arguments about decisions that are being made. So,
do you know why they chose depth first initially?
So it is Curtis's belief that you can solve all of these ills by adding more cues. And it is Phil's belief that this is epicycles.
Neil, are you
Yes.
cutting out? Is Neil cutting out for anyone else?
No.
No, it's good for me.
Oh, okay, it's me.
So I think depth first move ordering is going to happen, but the fact that the argument is happening is
Well, you mean breadth first, right?
or excuse me, breadth first is going to happen.
I was going to say, isn't Minden working on that?
Yeah, I mean it's I think it's like almost done.
Yeah.
So yeah, Scott, are you working on it?
Yeah, what is? Yeah.
Breath first is done. Ticks are getting close to being done.
Ticks are the markers of like how far you are in. Is that right?
Essentially.
Yeah.
So if, say you've got a list of 11 events that you're handed, and some of those events might actually not produce indirect events, right?
Right. Is there a question there? Was there a question, or I think you might be cutting out. Yeah, I'm not getting anything from you, Matt. So I'm going to press ahead. The other thing in the grab bag is OTAs. How do OTAs work? So fundamentally, the highest level, you're transmitting a new noun to Arvo describing the new state and the transition rule that you need to follow. In practice, there are three possibilities for when an upgrade command gets sent to Arvo. So this will actually come into Arvo in what? Here, this is update engine. This is in the I believe it's in the 3BE. No, this isn't. This is in the excuse me, the other core, not the formal interface, whatever the other core was called. I forget what I named it when I was putting it in the notes, but this is the other one. So we get a maybe initiate a kernel update, continue with kernel update, or update the modules. These are the kinds of things that you care about possibly doing here. So there's three possibilities when you get this noun. You're going to get a bunch of Hoon source in what, and you have to decide what to do with it. So one option is that you have the same version, or the list is empty. So you get an empty list of Hoon, which means you've either done everything or you're already at the version that was requested. Another one is that there's no Arvo change. This is like if you're upgrading Veins or Lol and Zeus. And the other one is that you have a new Arvo kernel. And this can include a language change. So Arvo knows about FAS/sys, and it knows about relative precedence of Hoon, Arvo, Lol, and Zeus, and Veins. So it can rebuild based on this topology smartly. It doesn't need to rebuild everything. If only Lol and Zeus or a Vein changes, case 2, then you only need to build those new cores and then provide them as inner cores for the new system. On the other hand, if Hoon or Arvo change, then you need to build a new Hoon, compile a new Arvo against it. Then what you do is you gather all the persistent and ephemeral state plus the new upgrade state, and you hand that to the new Arvo core. The goal of Arvo is to get itself into the new world as quickly as possible and then let the new world process everything. This is actually one of the places where depth first versus breadth first makes a difference. Depth first means that you always have to pass a work list of moves to new Arvo because there may still be moves to run. And this is a constraint on new Veins because they may still always have to handle old world moves. So there may be in their work list moves that were generated by old world Arvo from the depth first that are stored in this work list that they still have to be able to process. If you switch to breadth first, this means that you'll have more flexibility. You'll be able to generate moves for the targeting the new world vein that will not be processed until Arvo has been upgraded. Concretely, what happens stepwise is Arvo learns a new version exists. Okay, that's the first part. You receive a notification from someone you're subscribed to, a publisher you're subscribed to. You learn this new revision exists. Then Clay over Ames gets the metadata, retrieves the metadata about it. Then Fine retrieves individual files. And we like Fine for that because the remote scribe protocol means that you can check out, desk updates to base directly from the serving runtime rather than hitting Arvo. And in that case, you don't generate spurious events and overhead on the publisher side. So once you have that data, then you start the commit. So then Clay starts commit process in Park. So if we go to Clay, We can see what happens with Park. And some of this we'll circle back around to next time when we talk about upgrades too. But what Park does ultimately is it has some state for the pending blob store, etc. That's what it's doing here. The blob store is a content addressed storage of the data, the nouns that it knows about for the upgrade. This is actually one place, Ted mentioned this earlier, where slip comes in handy. I'm looking for sys update, which is somewhere right after all this. Yeah, there's the sys update here. What the sys update does is it builds everything, and it's going to slip a fork to Clay. This is a place where we actually want to slip it because we want Arvo to finish the upgrade, and then you want it to run Clay with an empty task, which is a fork task, which is a continuation. So then Clay goes right back to process, it goes right back into the same arm Park and continues where it left off in the commit process with the information that it had about the ephemeral state. So that's what's going on with the system upgrade with Arvo. Probably the most complicated thing that can happen with all of this is if you are changing type, right? So if you're actually changing the definition of type, this is going to impact vase mode, which means you have to kick back up into metavases. And this is what the old Arvo's cum vein used to handle. But you can do it all in untyped mode. The update has to be an untyped knock formula from the perspective of the old kernel. And in the new world, it is ordinary typed code, which is this kind of this weird thing that you have to deal with here. So we'll look at a little bit more of that with the boot process next time, and we'll see how those handle. So that's what's going on with an OTA. That's the information that you're transmitting when you do an OTA. Now, okay. Homework from this time. I think this is a pretty interesting one. One part of it's kind of boring. I think the other one's like pretty cool, pretty interesting. The first part's going to be annotating a move trace, like producing a move trace from a generator invocation with bar verb, and then just sort of like tracking. There's a move trace tutorial you can follow, and you want to do something similar to that of just like, okay, I'm tracking what's going on with these values being given around and passed around. The next part is going to be producing a baby pill, producing a functional minimalist Arvo core that can actually boot on Ver. So you're going to have to produce a gate that produces a core with those 4 arms with the correct type signature. There's a video that I'll link you where Phil did this. So I know Amadeo and Matt have done this because Phil did it with them in the video a few months back. But this is what you're going to do. So you can actually produce a pill of a no-op Arvo shaped noun that you can run on a new Ver. And so that's going to be the next thing we'll do with the homework there, which is kind of a neat operation. And that's it for mature Arvo. So next time we'll dig into the boot process and Larval Arvo and what's going on with that before we turn our attention to the runtime itself and all of this.